Good morning, AP Stat. This is the last section of Chapter 15. Continuous random variables is our topic for the day. So up to this point, we've been talking about discrete random variables. Now we're going to be talking about continuous random variables, who are similar to discrete random variables in some ways, but they do have a key difference. And it's going to be a difference that shows up when we do calculations on our graphing calculators. So up until now, we have discussed discrete random variables. Those are random variables whose outcomes are countable and finite. So we recall that the random variable can assume any real number on an interval when it's a continuous random variable. So continuous random variables can assume any real number value on an interval. That is not a countable set. If you were to go to the lowest possible value and try to find the next highest possible value in that interval, you couldn't do it because literally, strictly mathematically speaking, it doesn't exist. So it is uncountable. You literally can't count the set of values in that list, but there are variables that behave like that, and they are not uncommon. If we considered the variable top speed of car X, then the set of outcomes would be, say, 0 miles an hour for a stationary car to 316 miles an hour. As of 2020, the SSC2 Atara, which you see pictured at the bottom right, is the fastest roadworthy car. By the time you're seeing this slide, it may well be something else. Unless otherwise specified, continuous random variables have the same properties as discrete random variables. So that's good to keep in mind. All the properties we learned about with discrete random variables apply to continuous random variables unless I make an exception. Also, and this is big, this may seem kind of out of left field right now, but this is a big deal. If two independent continuous random variables both have normal models, all right, so if they both fit a normal model, so does the sum or difference of those random variables. So if I have two random variables and they fit a normal model themselves, then the sum or difference of those variables also can be modeled with the normal model. That is a huge deal, and we will see that later in this lesson. So we'll keep that in our back pocket, save it for later. So here's our first practice problem. There are a couple unnecessary lines in this problem, so I'm going to skip down a little bit. The times required to pack these home theater systems that we're going to be talking about can be described by a normal model with a mean of 9 minutes and a standard deviation of 1.5 minutes. So the time to pack has a mean of 9 minutes and a standard deviation of 1.5 minutes. The times for the boxing stage can also be modeled as normal with a mean of 6 minutes and a standard deviation of 1 minute. Okay? So we have two parts of the process for these home theater systems. We have the packing stage and the boxing stage, all right? And this is putting them in boxes, not putting them in a ring with boxing gloves, of course. What is the probability that packing two consecutive systems takes over 20 minutes, all right? So we're talking about packing, not boxing, and taking over 20 minutes. So how do we do this? Well, here's how the textbook breaks it down. You want to estimate the probability that packing two consecutive systems takes over 20 minutes. So we have a total time to pack the two systems. And then P sub 1 is the time for packing the first system. P sub 2 is the time for packing the second. Just like before, just like in the last video, we want to acknowledge that these two systems constitute two different random variables that follow the same rules. We can't just say 2 times P, all right? We need to acknowledge P1 and P2 as separate random variables that follow the same rules. They both follow the rules of P for packing, but we need to acknowledge that the total time packing constitutes a sum of random variables, not just doubling the packing time of one, all right? It would not change the expectation if we used 2p, but it would change the standard deviation by quite a bit. So we need to be careful there. So these are two different systems, two different p's. Moving on. There are a couple assumptions we have to lay out. The normal model assumption. We're told that both random variables follow normal models. It's right in the problem. and the independence assumption. We can reasonably assume that the two packing times are independent. This is going to allow us to do this problem. We're only able to find the variance and standard deviation of a sum of random variables that we see here if, in fact, those two random variables are independent. The time spent packing one does not affect the time spent packing the other, and we are free to make that assumption. All right, so moving on, here's the actual problem-solving part. The expectation for the total time is the expectation of the sum of the packing times, which is the sum of the expectations for each packing time, 9 minutes each, as the problem says, 9 minutes each, makes for 18 minutes. Because the times are independent, we're able to find the variance and standard deviation. I'm going to jump right to the standard deviation. The standard deviation of the total time to pack the two systems is the standard deviation of the sum of the packings, all right? Which is equal to the square root of the sum of the squares of the standard deviations. It's the square root of the sum of the variances. We know that 1.5 minutes is the standard deviation for packing. So I would substitute 1.5 into standard deviation of P1 and P2, and I would get 2.12 minutes approximately. So I need my expectation and my standard deviation in order to solve this problem. So the first thing you should do after what you saw on the first slide, laying out our assumptions, making sure we're able to do this problem, and a bit of labeling P1, P2, and T, if you feel so led, is to find the mean and standard deviation. And the reason we need to do that is because we're going to be reacquainting ourselves with an old friend called normal CDF. So we are going to use the model, normal model, centered at 18, standard deviation of 2.12, and we want to find the odds of being above 20 minutes. The mean is 18, standard deviation is 2.12. What are the odds? What's the area over here in red that we are above 20 minutes? Now, what's this 0.94 over here? That is a z-score. There's a way of doing this problem that has you use a z-score. It's not the most efficient way. I just figured you want to know what that is. But it is labeled in the book, and it's tough to crop out, so I didn't even bother. But that is a z-score associated with 20 minutes. That would be 20 minus 18 divided by the standard deviation of 2.12. It's about 0.94. All right, moving on. So we have enough information to use normal CDF. So for here, we use normal CDF, and here are our inputs. We want to see what are the odds of being above 20. So 20 is our lower bound. Our upper bound is non-existent, so we just use an arbitrarily high number. 10 to the 99 will work just fine. The mean is 18, standard deviation is 2.12. Time for the calculator. So we're here at the calculator. I'm going to go to second distribution. I'm going to go to number 2, normal CDF, and I'm going to start entering some things. I want to have my lower bound be 20. My upper bound, I'm going to make 10 to the power of 99. And I'm going to have my mean be 18 and my standard deviation 2.12. And then I go down to hit paste. And I get a little north of 17%. Okay, on to the next problem. A little bit of a different scenario than before. What percentage of the theater systems take longer to pack than to box? All right? Take longer to pack than to box. This time we're going to be analyzing a difference. And we want to find the difference between packing and boxing, those two different random variables. We want to find the probability that packing minus boxing is greater than 0, right? The probability that packing minus boxing is going to be greater than 0. So here's how we set it up. P is the time for packing, B is the time for boxing, two different random variables, and D is going to be the difference in times to pack and box a system. So the time, the difference for packing and boxing is obviously P minus B. And we want to find the odds that P minus B is greater than 0. In those instances, packing takes longer than boxing because P and B model the times to pack and box respectively. Got to check our assumptions. Both assumptions check out. We are told that random variables follow normal models, and we assume that that the times it takes to pack and to box a system are independent, all right? And there's something I didn't note before. Remember in the very beginning I said that if two variables follow normal models, their sum or difference follows a normal model? That's what's making these problems possible. P follows a normal model, B follows a normal model, therefore P minus B, just like P plus B in the last problem, follow a normal model as well. So a sum or difference of variables that follow normal models also follows a normal model. And that's why we're able to model the difference or the sum of variables using a single normal model. It's a huge break that we catch because of the usefulness of the normal model. So let's get to work. The expectation for the difference is going to be 3 minutes. We have 9 minutes spent packing on average, 6 minutes spent boxing. That'd be a difference of 3 minutes on average. Standard deviation of the difference is going to be the standard deviation of P minus B, all right? Which, if we're finding the standard deviation of a difference of random variables, it does not matter that it's a difference. We still add the variances together, the squares of the standard deviations, and then square root to find the standard deviation of a difference of random variables. When we're talking about variances or standard deviations, whether we're adding or subtracting variables, we are introducing new variation either way. All right, so the variation is going to increase regardless of whether the sign is plus or minus. Hopefully I've driven that point home. So we say standard deviation of packing. Now the standard deviation of packing is 1.5 minutes. And I don't know why I put it second over here, so I'll just make that note. The standard deviation of packing is 1.5, and the standard deviation of boxing is 1. Addition is commutative. The order doesn't matter. Just didn't want to confuse you there. All right, so we add all this together, and we get about 1.8 minutes after the square root. So we have a mean of 3 minutes for the expectation for the difference, and a standard deviation of 1.8 minutes for the difference of packing and boxing. Now we're going to go to our normal model again. Our mean is going to be 3, standard deviation is about 1.8, and we want to find the odds that we are above 0. Okay, so here we go. So we're back at the calculator again. Let's get to work. We want to find the odds of, so 0 is our lower boundary. And our upper boundary is 10 to the 99. The mean is 3, and the standard deviation is 1.8. We hit paste. That gives a pretty high probability, over 95% chance that packing takes longer than boxing. And here's your homework. A lot of hints for this one that I've thrown in over the years, so pay close attention to that. Have a good day.